Hey there, curious minds. Have you ever, looked at a box of Fruity Pebbles and wondered what gives it that super bright, almost neon color? Or maybe thought about how a simple chemical reaction was actually key in discovering some really early life-saving drugs?
It's pretty fascinating when you think about it, isn't it? Today, we're taking a deep dive into the world of aromatic substitution reactions. These are, the sort of unsung heroes behind so many compounds we see and use every day. We'll explore how these fundamental processes actually work, why they behave the way they do, and how chemists strategically use them to build really complex molecules.
Think of this as your VIP pass to understanding a really core pillar of organic chemistry. We're going to unpack the key concepts, the mechanisms, the real-world applications. Got to cut through the jargon to give you those aha moments. So grab your mental lab coat, maybe, because you're about to get genuinely well-informed on a topic that touches, well, almost everything, from food to medicine. Okay, let's maybe kick things off with the absolute foundation, electrophilic aromatic substitution, or EAS for short. Now, you might know that regular carbon chains, especially those with double bonds, alkenes, they react pretty easily. They'll add something like bromine, no problem. But then you look at benzene, that famous six-carbon ring, and surprisingly, under those exact same conditions, it just sits there. It's, well, inert. Why is it so stubborn?
That's the classic benzene paradox. Its remarkable stability comes down to something we call aromaticity. You can kind of picture it as this perfectly balanced, super stable electron highway running around the ring. If you just try to add something across a double bond like you normally would, you'd break that whole stable system. And the molecule really doesn't want to do that. The energy cost is just too high.
But okay, here's where it gets really interesting. If you toss in a little helper chemical, often a metal like iron, with that benzene and bromine, suddenly a reaction does happen. But it's
Okay.
not addition, it's a substitution. So one of benzene's original hydrogen atoms gets swapped out for, say, a bromine atom, and crucially, that stable aromatic ring system, it stays intact.
Exactly. It's preserved, and this happens in basically a two-step dance. First step. The aromatic ring, which has plenty of electrons, acts as a nucleophile. It attacks an electron-poor species, the electrophile. We call it E+. This forms a positively charged intermediate called a sigma complex, or sometimes an uranium ion. Now, this step takes energy because you do temporarily lose that aromatic stability. The ring kind of holds its breath.
Okay, so it forms this unstable thing.
Right. Then, step two. Something acting as a base comes along, maybe another molecule in the mix, and it plucks off a proton, a hydrogen ion, from the carbon or the electrophile attached. And boom! Those electrons snap back into the ring, restoring that precious aromaticity. The ring can breathe again.
And the electrophile is now attached. So substitution wins because it keeps that special stability in the end. Addition would lose it permanently.
Precisely. It's thermodynamically much more favorable to substitute.
All right, so we've got the general idea. Let's talk about some specific types of EAS reactions. First up, halogenation. Putting a halogen, like bromine or chlorine, onto the ring.
Yeah. For this, you need the halogen molecule itself, like Br2 or Cl2, and you also need a Lewis acid catalyst. Think things like iron tribromide, Ferber3 for bromination, or aluminum trichloride, AlCl3 for chlorination.
And the Lewis acid isn't the direct catalyst, right? It
Right.
sort of activates the halogen.
Exactly. It reacts with the Br2 or Cl2 to generate a much more powerful electrophile, something that behaves like Br plus or Cl plus as well. It makes the halogen really hungry for the ring's electrons.
Are there limits? Like, can you do this with fluorine or iodine?
Good question. Fluorination tends to be way too reactive, almost violent, and iodination is often just too slow and doesn't give great yields, so Bri and Cl are the main players here.
Okay. And you mentioned real-world impact, like in drugs.
Oh, absolutely. Halogenation is critical in modifying drug structures to improve them. Take an older antihistamine, phenyramine, stick a chlorine atom on its aromatic ring in just the right spot, and you get chlorphenyramine.
And that's better.
10 times more potent. Just from adding one chlorine, you also see this in antifungal agents like clotrimazole or iconazole. The exact position of the halogen orthopara is crucial for how well they work.
Wow. Okay, next reaction. Sulfonation. Adding an SO3H group.
That's the one. You add a sulfonic acid group. The reagent is usually fuming sulfuric acid, which is basically sulfuric acid, H2SO4, with extra sulfur trioxide, SO3, dissolved in it. And that SO3, sulfur trioxide, is the electrophile here. It's a really powerful one because the sulfur atom is highly electron poor due to those oxygen atoms pulling electrons away.
So it strongly attracts the benzene ring.
Very much so.
And the Fruity Pebbles connection, how does that fit in?
Right. So many common food colorings like red number 40 and yellow number 6, maybe check the box next time, are aromatic compounds. They have these sulfonic acid groups, the SO3H groups, attached.
Why? What do they do?
They make the dye molecules water-soluble, which is essential, if you want the color to actually dissolve in your food or drink. Without sulfonation, they wouldn't mix properly.
Huh. Never thought about that. Makes sense.
And a really key feature of sulfonation, something we'll come back to, is that it's reversible. You can put the group on and you can take it off again under the right conditions. That's a handy trick.
Okay, noted. Reversible. What's next?
Nitration. This installs a nitro group, NO2, onto the ring.
How's that done?
You use a mixture of nitric acid, HNO3, and sulfuric acid, H2SO4. Here, sulfuric acid is actually the stronger acid, and it protonates the nitric acid. This generates the real electrophile, which is the very potent nitronium ion, NO2 plus O.
NO2 plus O, got it.
Yeah.
And why is nitration useful?
It's a fantastic gateway reaction in synthesis. Once you have that NO2 group on the ring, it's relatively easy to reduce it down to an amino group, NH2. You can use reagents like iron or zinc metal with hydrochloric acid, followed by a base.
So nitrate first, then reduce.
Yeah.
And you've got an amino group on the ring.
Exactly. It's a standard two-step method to install amino groups, which are building blocks for many other things like dyes and pharmaceuticals.
And this links to another medical story, right? Prodrugs.
Yes, a huge one. Early chemists studying azodyes, which often contain nitrogen groups, stumbled upon a compound called Prontosil. It showed amazing antibacterial activity, but only in vivo inside a living animal. It didn't work in a petri dish, in vitro. Very puzzling.
Strange. Why would that be?
It turned out Prontosil itself wasn't the active drug, it's a prodrug. The body's metabolism actually breaks it down, chemically transforms it into the real active compound, which was identified as sulfanilamide.
Wow, so the body activates the medicine.
Precisely. This discovery of the prodrug concept was revolutionary for medicinal chemistry. It led to the development of thousands of other sulfonamide sulfa drugs and fundamentally changed how we design medicines to be delivered effectively in the body. Think about L-Dopa for Parkinson's. That's also a prodrug designed to get into the brain.
Amazing. All starting from studying colored compounds. Okay, moving on. What about adding carbon chains?
Yes. The Friedel-Crafts reactions, named after Charles Friedel and James Crafts, who discovered them back in 1877. First, there's Friedel-Crafts alkylation. This reaction lets you attach an alkyl group, basically a carbon chain, directly to the aromatic ring.
How does that work? What do you need?
You take an alkyl halide, like an alkyl chloride, ArCl, and you react it with the aromatic ring in the presence of a Lewis acid, typically aluminum trichloride, AlCl3. The Lewis acid helps rip the halogen off, generating a positively charged carbon species, a carbocation, R+, which is the electrophile that the ring attacks.
Okay, seems straightforward enough.
Yeah.
You mentioned limitations earlier. Sounds like there's a catch.
Oh, there are several big catches. Common pitfalls for students, actually. First, carbocation rearrangements. If you start with a primary alkyl halide, the carbocation that forms initially is often unstable. It can and often will rearrange itself internally through hydride or alkyl shifts to form a more stable secondary or tertiary carbocation before it even reacts with the ring.
So you don't get the product you expected.
Exactly. You often get a mixture of products with the rearranged alkyl group attached, so direct alkylation is really only reliable if rearrangements are impossible for that specific alkyl group.
Okay, rearrangements. What else?
Second, the carbon atom attached to the halogen in your starting material must be sp3 hybridized, regular alkane-like carbons. Vinyl halides or aryl halides, where the halogen is attached to a double-bonded carbon or directly to another aromatic ring, just won't react.
Got it. It's FD3 carbon only.
Third, polyalkylation. The alkyl group you just added actually makes the ring more reactive than benzene itself.
Oh, so it encourages more alkyl groups to add on.
Yes.
Yeah.
It activates the ring towards further alkylation. So it can be hard to stop the reaction after adding just one group. You might get di- or trialkylated products, although you can sometimes control conditions to favor monoalkylation.
Tricky. And the last limitation.
A big one. Friedel-Crafts reactions, both alkylation and the next one we'll discuss, do not work on aromatic rings that are already moderately or strongly deactivated. So if your ring already has an electron withdrawing group on it, like a nitro group, NO2, forget about doing Friedel-Crafts. The ring is just too electron poor to react.
Okay, those are some significant hurdles for alkylation. Is there a better way?
Often, yes. That brings us to Friedel-Crafts acylation. The goal here is to install an acyl group, which is a carbonyl group, CO, attached to an R group.
So RCO gets attached to the ring. What are the reagents?
Similar idea, you use an acyl chloride, RCOCO, and a Lewis acid, again, usually AlCl3. This generates the electrophile, which is called an acylium ion, RCO+.
And what's special about this acylium ion?
It's incredibly stable due to resonance. It has a resonance structure where every atom has a full octet, including a triple bond between carbon and oxygen, and because it's so stable...
It doesn't rearrange.
Exactly. That's the big advantage. Acylium ions do not undergo carbocation rearrangements. This is a massively important problem-solving technique in synthesis.
So if you want to add a specific alk group, but direct alkylation would cause rearrangements.
You can do it indirectly. First, perform Friedel-Crafts acylation to install the corresponding acyl group. That goes on cleanly without rearrangement. Then you do a second reaction called a Clemmensen reduction using zinc amalgam and HCl with heat, which specifically chops off the carbonyl oxygen, reducing the CO down to a CH2.
And you're left with the alkyl group you wanted, attached cleanly. Very clever.
It's a standard two-step workaround for the rearrangement problem. Plus, there's another advantage to acylation.
What's that?
Remember how alkylation suffered from polyalkylation because the alkyl group activates the ring?
Yeah.
Well, the acyl group you add during acylation actually deactivates the ring towards further reaction.
Oh, so you don't get multiple acyl groups adding on.
Correct. Polyacylation is generally not observed. You get clean monoacylation. So 2 big wins, no rearrangements and no polyacylation.
Makes Friedel-Crafts acylation sound very useful, especially with the reduction step afterward.
It absolutely is, a cornerstone of aromatic synthesis.
Okay, great. So we know how to put groups onto a plain benzene ring. But what if there's already something attached? You said it acts like a traffic cop.
Exactly. An existing substituent on the ring dramatically influences what happens next. It affects 2 key things. 1, the rate of the next reaction. Does it make the ring react faster, activation, or slower deactivation compared to benzene itself? And 2, the regiochemistry. Where does the next group attach? To the position right next door, ortho, across the ring, para, or one position over meta?
Activation, deactivation, and ortho-para-meta directing. Got it. Let's start with activating groups.
Okay. Most activating groups are also ortho-para directors. Take a simple methyl group, like in toluene methylbenzene. Methyl groups are weakly activating. Toluene reacts like 25 times faster than benzene in nitration.
Why does it activate?
It donates a little bit of electron density into the ring through a subtle effect called hyperconjugation. It makes the ring slightly more electron-rich and inviting to electrophiles.
And why ortho-para directing?
Because when the electrophile attacks at the ortho or para positions, the positive charge in that sigma complex intermediate can be better stabilized by the methyl group. Attack at meta doesn't get that extra stabilization. So ortho and para pathways are lower energy.
Makes sense. What about stronger activators?
Groups with atoms that have lone pairs directly attached to the ring are much stronger activators. Think of a methoxy group, OCH3, like in anisole. Oxygen is normally electron withdrawing, but here its lone pair can donate electron density directly into the ring through resonance. This effect is much stronger than induction.
So it really pumps electrons into the ring.
Yeah. Anisole nitrate's about 400 times faster than even toluene. And like the methyl group, it's also strongly orthopara, directing for the same reason resonance stabilization of the intermediate for orthopara attack.
So the rule seems to be activating groups direct orthopara.
That's the general rule. All activators are orthopara directors.
Okay, what about the opposite? Deactivating groups.
Right. Deactivating groups pull electron density out of the ring, making it less reactive, and most of them are meta-directors. The classic example is the nitro group, Mechanistic on nitrobenzene. It's a powerful deactivator. Nitrobenzene reacts, get this, about 100,000 times slower than benzene.
Wow, why so slow, and why meta?
It deactivates through both induction, the positive nitrogen pulls electrons, and resonance, which puts positive charges inside the ring. It makes the ring very electron poor. Now, why meta-directing? Well, attack at any position is unfavorable compared to benzene, but attacking ortho or para would place the positive charge in the sigma complex right next to the already electron-deficient nitro group, a really bad situation, like charges repelling. Attacking at the meta position avoids putting that positive charge directly adjacent to the nitro group. It's still deactivated, but it's the least bad option energetically.
So the meta pathway is the least destabilized.
Exactly. So the rule here is most deactivators are meta-directors.
Most. Is there an exception?
Yes. The curious case of the halogens, chlorine, bromine, iodine.
What's weird about them?
They are unique. Halogens are actually deactivators. They pull electron density out of the ring overall, mainly through induction, making the ring less reactive than benzene.
Okay, so they slow the reaction down.
But they are orthopara-directors.
Wait, what? A deactivator that directs orthopara? How does that work?
It's a bit counterintuitive. While their inductive effect withdraws electrons and deactivates the ring overall, they do have lone pairs. These lone pairs can provide some resonance stabilization to the positive charge in the sigma complex, but only when the attack is at the ortho or para positions. So even though the whole ring is less reactive, the ortho and para pathways are less destabilized than the meta pathway because of this weak resonance help from the halogen's lone pairs.
So induction wins for overall reactivity, deactivating, but resonance wins for directing effects, orthopara.
That's a good way to put it. Halogens are the key exception to memorize. Deactivating, but orthopara directing.
Okay, this is helpful. Can we categorize these groups, like strong versus weak?
Absolutely. Chemists group them. Strong activators. Have a lone pair right next to the ring that strongly donates into the ring, like OH and H2. Moderate activators. Lone pair next door, but maybe it's also involved in resonance outside the ring, or alkoxy groups, RR. Weak activators. Alkyl groups like Nager's CH3. Weak deactivators. The halogens, F, DAX-Cl, DAX-BRF. Moderate deactivators, groups with a pi bond to an electronegative atom conjugated with the ring, like carbonyl-CO, sulfonyls SO3H, nitryl-CN. Strong deactivators, groups with a full positive charge next to the ring, or highly electron-withdrawing groups, like NaGeC and O2, NaCNR3 plus DAAGL3.
That framework is really useful for predicting reactivity in regiochemistry.
Definitely.
Okay, what if you have multiple groups already on the ring? How do you decide where the next one goes?
Good question. Sometimes the groups cooperate, they both direct to the same positions. That makes it easy.
But if they conflict, like one wants orthopara and the other wants meta,
Then the rule is, the more powerful activating group wins and controls the directing effects. So strong activators override weak activators, and any activator overrides any deactivator when it comes to deciding where the new group goes.
makes sense. Power rules. What about space? Steric effects.
Ah, yes. Sterics play a big role too. Generally, attack at the para position is favored over the ortho position simply because there's less crowding. It's easier for the electrophile to approach. Although for small groups like methyl, the ortho-para ratio can vary.
And if the ring already has two groups?
Substitution will generally prefer the position that is less sterically hindered. Avoid the crowded spots. And here's a crucial steric rule. If you have two substituents meta to each other, a 1-3 dissubstituted ring, substitution is extremely unlikely to occur at the position between those two groups. It's just too sterically blocked.
Okay, avoid the spot between metasubstituents.
Yeah.
Good tip. Now, you mentioned sulfonation being reversible and useful as a trick. Blocking groups.
Yes. Sometimes the regiochemistry rules work against you. Maybe the major product according to electronics and sterics is para, but you really want the ortho product. This is where blocking groups come in. Remember, sulfonation installs the NADSO3H group and is reversible. You can temporarily install that NADSO3H group at the position you don't want the main reaction to happen at, for example, the para position. This blocks that site. Then you carry out your desired reaction, like nitration or halogenation. Since the preferred parasite is blocked, the electrophile is forced to go to the next best spot, which might be the ortho position you wanted.
And then you just remove the blocking group.
Exactly. Because sulfonation is reversible, you can easily remove the NADSO3H group afterwards, leaving you with your desired, otherwise minor, product. It's a very clever strategy.
That is clever. Okay, let's talk synthesis strategies, putting it all together.
Right. If you're making a monosubstituted benzene, it's usually straightforward, just pick the right EAS reaction. Remember, though, some groups need two steps, like making an amino group via nitration then reduction, or an alkyl group via acylation then reduction to avoid rearrangements.
But for dissubstituted rings, the order matters hugely.
Critically, you absolutely must consider the directing effects of the first group when planning how to add the second group. For example, if you want to make bromine meta to an amino group, you can't just put the amino group on first because it's orthopara directing.
Right, so you'd nitrate first.
Exactly. Nitrate first, NO2 is metal directing. Then brominate, bromine goes meta to NO2. Then reduce the NO2 group to the NH2 amino group. The order is key.
That makes sense. You use the directing effects to your advantage. Are there any big don'ts in synthesis planning?
Yes, a couple of crucial limitations to always remember. One, You cannot perform nitration if the ring already has an amino group, NaSH-NH2. Nitric acid is an oxidizing agent and will just oxidize the amino group, causing side reactions. You'd typically protect the amino group first if you needed to nitrate.
Okay, no nitrating anilines directly.
2. As we mentioned with Friedel-Crafts, you cannot perform Friedel-Crafts alkylation or acylation on rings that are moderately or strongly deactivated. If you have a nitro group, sulfonic acid group, carbonyl group, etc. already on there, Friedel-Crafts is off the table.
Got it. Important limitations. So for really complex molecules with many substituents.
Chemists often use retrosynthetic analysis. You start with the target molecule and work backward, mentally breaking bonds and changing functional groups, always asking, what precursor could I make this from using reactions I know?
You keep working backward until you reach simple starting materials, always considering the electronic, steric, and ordering factors at each step. It's like solving a maze in reverse. Okay, wow. We've covered a lot on electrophilic aromatic substitution, but you hinted there are other ways aromatic substitution can happen.
Indeed, the script slips sometimes. Instead of the ring attacking an electrophile, the ring can be attacked by a nucleophile. This is nucleophilic aromatic substitution, or SNAR.
So the ring gets attacked by something electron-rich. How does that work? Doesn't the ring already have lots of electrons?
It does, which is why SNR doesn't happen easily. It needs very specific circumstances. There are 3 strict criteria. 1, the ring must have a powerful electron-withdrawing group on it, usually a nitro group. This makes the ring electron-poor enough to attract a nucleophile. 2, the ring must contain a leaving group, typically a halogen like Cl or Br, that the nucleophile can displace. 3, and this is crucial, the leaving group must be positioned ortho or para to that strong electron-withdrawing group. If it's meta, the reaction generally doesn't happen.
Ortho or para only? Why that specific positioning?
It's about stabilizing the intermediate. When the nucleophile attacks, it forms a negatively charged intermediate, sometimes called a Meisenheimer complex. That electron-withdrawing group, like NO2, is essential for stabilizing this extra negative charge through resonance. It acts like an electron sink. But it can only effectively do that if the charge can delocalize onto it, which only happens if the attack occurs ortho or para to it.
Ah, so the nitro group needs to be in the right place to help hold that negative charge. If it's meta, it can't really help stabilize it.
Precisely. That explains the strict ortho-para requirement for SNAR.
Okay, so that's SNAR, needs an electron withdrawing group and a leaving group, ortho or para. Is there yet another mechanism?
There is one more Meiji pathway, which happens under even more specific and usually quite harsh conditions. It's called elimination addition, and it involves a very strange intermediate.
What conditions trigger this?
This happens if you try to react an aryl halide, like chlorobenzene, with a very strong base, like sodium hydroxide at extremely high temperatures, or sodium amide, NaNH2, at lower temperatures, especially if the ring lacks those strong electron withdrawing groups needed for sonar.
And what was puzzling about it?
Early experiments using isotopes showed weird results. For instance, if you started with chlorobenzene labeled with carbon-14 at the carbon attached to the chlorine and reacted it with a strong base, the incoming group, like an amino group from NaNH2, ended up attached not just at the original carbon, but also split 50-50 between that carbon and the one next door, the ortho position.
That is weird. How could it attach next door?
The only way to explain this scrambling was to propose a highly unstable, short-lived intermediate called benzene. Benzene isn't like normal benzene. It's formed by an elimination step where the strong base rips off a proton ortho to the halogen, and then the halogen leaves, forming a species that has, effectively, a strained triple bond within the aromatic ring.
A triple bond in a benzene ring. That sounds incredibly strained.
Extremely strained and reactive. Then in the addition step, the nucleophile, like NH2, can attack either end of that reactive benzene triple bond with roughly equal probability.
Oh. And that explains the 50-50 mixture of products attacking one end gives substitution where the halogen was, attacking the other end gives substitution next door.
Exactly. It beautifully explains the isotopic labeling results. And chemists even managed to trap this fleeting benzene intermediate by reacting it with other molecules like furan in the Diels-Alder reaction, providing strong evidence for its existence.
Wow. Benzene. Okay, so we have EAS, SNAR, and elimination addition via benzene. That's quite a toolkit. How do you tell which mechanism is likely operating in a given reaction?
It comes down to looking at the conditions and the structure. You can use sort of decision tree. First, look at the attacking reagent. Is it an electrophile, electron poor? If yes, it's almost certainly EAS.
Okay, electrophile means EAS. What if it's a nucleophile?
If the reagent is a nucleophile, electron-rich, then you check the aromatic ring. Does it meet all three SNAR criteria? That is, 1, strong electron withdrawing group present, 2, good leaving group present, 3, are they ortho or para to each other?
And if all three are yes,
Then it's SNAR.
what if it's a nucleophile but the SNR criteria aren't met? Maybe no strong withdrawing group or the leaving group is meta.
Then you look at the conditions. Are they extremely harsh, very strong days, high temperature? If yes, then you suspect the elimination addition benzyne mechanism.
Electrophile das EAS. Nucleophile plus SNR criteria no SNR. Nucleophile plus no SNR criteria plus harsh conditions das benzar.
That's a pretty reliable way to approach it. You also see key differences in what gets substituted: a proton in EAS, a leaving group in SNR, and effectively a proton and a leaving group eliminated, then a nucleophile added in the benzyne route. And remember the opposite effects of electron withdrawing groups bad for EAS, essential for SNR.
That really clarifies the landscape. It's amazing how these different pathways allow aromatic rings to react under such diverse conditions. So there you have it. From the vibrant colors in your breakfast cereal, believe it or not, to the really intricate synthesis of life-saving medicines, the world of aromatic substitution reactions is, well, truly profound. We've seen how seemingly simple principles, like electron flow and stability, dictate these incredibly complex outcomes, and how chemists learn and use these rules to build almost anything they can imagine.
Exactly. And it's not just about, memorizing a list of reactions. It's really about understanding the why behind them. Why does one group direct orthopara? Why does another direct meta? Why won't a certain reaction work at all under specific conditions? How can a subtle change unlock a completely different pathway, like using a blocking group? That level of precision, that understanding, is what makes organic chemistry such a powerful and creative tool.
Yeah. So maybe as you go about your day now, you might look at an ingredients list or think about the structure of a medicine and actually see these reactions playing out in a whole new light. And maybe that brings us to our final provocative thought for you, the listener. Knowing now how precisely chemists can control these reactions, directing atoms to specific spots on a ring, what seemingly impossible molecular structures could you now imagine synthesizing? What molecule could you design using these principles to maybe tackle one of the world's grand challenges? A new therapeutic, perhaps, or a material for sustainable energy?
It really just comes down to how you apply this knowledge, doesn't it? We certainly hope you've enjoyed this deep dive into aromatic substitution. And thank you so much for joining us on the deep dive. Until next time, keep exploring.